I will next describe carbohydrates, sugars, and saccharides. These terms are synonymous with each other. The general formula of unmodified carbohydrates is CxH2OY. Carbohydrates are polyhydroxyaldehydes or ketones, or those that hydrolyze to polyhydroxyaldehydes and ketones. The simplest carbohydrates are monosaccharides. Monosaccharides cannot be hydrolyzed further to simple carbohydrates. Disaccharides can be hydrolyzed into 2 monosaccharides. Oligosaccharides yield 2 up to about 20 monosaccharides. Polysaccharides, on the other hand, yield more than 20 monosaccharides. Please note that the cutoff number 20 is not set in stone. It may be smaller or larger depending on the type of carbohydrate being described. Carbohydrates are synthesized in plants by photosynthesis. Monosaccharides are classified according to the number of carbons and whether an aldehyde or a ketone group is present. For example, this compound here has 4 carbons and contains an aldehyde group. Hence, it can be called an aldotetrose. Aldo for aldehyde, tetrose for 4 carbons. Similarly, this compound here has 5 carbons and a keto group. It can be identified as a ketopentose. The simplest of sugars contain 3 carbons. They are glyceraldehyde, an aldotriose, and dihydroxyacetone, a ketotriose. Glyceraldehyde exists as enantiomers, whereas dihydroxyacetone is a chiral. Plus glyceraldehyde, or that form of glyceraldehyde which rotates plane polarized light clockwise, was designated as D. And minus glyceraldehyde, that form of glyceraldehyde which rotates plane polarized light counterclockwise, was designated as L. When this aldotriose is drawn using the Fischer projection with the carbonyl group on top, the OH group of D-glyceraldehyde is positioned on the right side, whereas the OH group of L-glyceraldehyde is positioned on the left side. For other types of monosaccharides, we similarly use these designations D or L if the highest numbered chirality center, we call it the reference atom, has the same configuration as the respective D or L glyceraldehyde. Hence, for the case of glucose, the highest numbered chirality center is this one, C5. And we only need to look at the configuration or the position of the OH group with regards to D-glyceraldehyde. If they are identical, we can designate this compound as D-glucose. By this system, we can call this as L-arabinose because the OH group is on the left side, similar to L-glyceraldehyde, and this compound is D-fructose because the OH group connected to the highest numbered chirality center is positioned on the right side. Glucose exists primarily in 2 cyclic hemiacetal forms that are diastereomers of each other. When this oxygen attacks this carbonyl group, cyclic hemiacetals are formed. These two hemiacetals differ in configuration at the newly formed chirality centers. They are called anomers, and we designate them as alpha or beta. The newly formed chirality center is called the anomeric carbon. These compounds are diastereomers. They have different melting points and different specific rotations. We designate the cyclic hemiacetal form of a monosaccharide as the alpha anomer if the oxygens at the anomeric center and the reference carbon are on the same side in a Fischer projection. On the other hand, we designate a cyclic hemiacetal form of a monosaccharide as a beta anomer if the oxygen at the anomeric carbon and the reference atom are on opposite sides in a Fischer projection. Fischer projections of cyclic monosaccharides are a bit unwieldy to look at and often is kind of confusing. Hence, other projections are utilized to represent the cyclic forms of monosaccharides. One type of projection is called the Haworth projection. Here we use hexagons, wherein the oxygen is positioned on the upper right-hand corner, and the anomeric carbon is on the right side. The atoms or groups bonded to the ring carbons are shown connected by vertical lines. We can relate the alpha-glucopyranose in a Fischer projection to a Haworth projection by rotating it clockwise and looking at the positions of the OH groups. Here, the OH group is on the right side, and here it's positioned downwards. This OH group is on the left side, and here it's positioned upwards. We can do this comparison similarly with beta-D-glucopyranose. Another type of projection is called the Mills projection, which also uses a hexagon. The difference here with Haworth is that the Mills projection uses the wedge and dashed lines to represent bonds that are oriented closer or far away from the viewer. For the case of the OH group at the anomeric position of alpha-D-glucopyranose, the Mills projection orients it far away from the viewer. The last type of projection is called the Reeves projection, and here the 6 membered rings are shown in chair conformations. For many monosaccharides, they may exist as 5-membered ring hemiacetals. We call those furanoses. Or 6-membered ring hemiacetals. We call those pyranoses. This is alpha-D-glucofuranose, a 5-membered ring type hemiacetal of glucose. And this is alpha-D-glucopyranose, a 6-membered ring type hemiacetal of glucose. In solution, the specific rotation of the alpha and beta forms of glucose change toward an equilibrium value of 52.7 degrees. Recall that each of these types of hemiacetals have unique specific rotation values. However, in solution, the alpha and beta forms may equilibrate to give an equilibrium value for specific rotation of 52.7 degrees. This process of change in specific rotation is called mutarotation. This equilibrium process involves the open form of the sugar. At equilibrium, glucose exists around 36% as the alpha anomer and around 64% as beta anomer. Mannose, a diastereomer of glucose, forms the alpha anomer at around 69% and the beta anomer at 31%. In the alpha anomer of these sugars, the OH group is in the axial position, and these values appear to favor the alpha anomer. This axial bias for anomeric substituents in sugars is called the anomeric effect. Glycosides are abundant in nature. These are acetals at the anomeric carbon of sugars. One example is the natural product salicine. This is an acetal of glucose, so we can call this as a glucoside. Acetals of mannose are called mannosides, and acetals of fructose are called fructosides. Glycoside formation is often acid catalyzed. Glycosides hydrolyze in acids but are stable in bases. The non-carbohydrate moiety in glycosides is called the aglycone. Of course, the carbohydrate component is called glycone.